Welcome to physics class on dimensions and its analysis of chapter number 2, units and measurement for class 11. And this is the part 3 of units and measurement. Part 1 and part 2 we have discussed length and breadth of all about the previous portion of that chapter number 2, and this is about dimensions and analysis. And in this dimension and dimensional analysis we will discuss all about concerning about this dimension and analysis. Now here dimensions means what we need to know the definitions of dimensions first. Dimensions means nothing but this is a physical this is dimension of a physical quantity are nothing but these are the powers to which the fundamental units of mass, length and time have to be raised to obtain its units. So here it is also given here that the dimensions of a physical quantity are the power to which the fundamental units of mass, length and time have to be raised in order to obtain its units. Okay. So we know that there are fundamental units and derived units, okay, of a physical quantity. So what happened? These fundamental units are nothing but these are mass, length, time, then thermodynamic temperature, electric current, then what are your amount of a substance, then what this luminous intensity. So these are all physical fundamental quantity: mass, length, time, then thermodynamic temperature, then what happened, this one your current, your amount of a substance, then your luminous intensity. These are all what fundamental quantities. Over and above this there will be also plane angle and solid angles, okay, and their units are nothing but for mass it will be what in an SI unit it will be meter, and its expression or its symbol will be capital M. Length will be used as L, time will be used as capital T, like this, okay, and your thermodynamic temperature will be expressed as or used by a symbol K, ampere, okay, by capital A. Ampere is a SI unit of electric current, and mole of a substance, okay, that will be denoted by MOL, mole. And then what happened, your luminous intensity, the SI unit is what candela, and it will be denoted by CD. So in mechanics we only require this one, mass, length and time. Others, when we require it, we will use it, okay. Now this for to find out what the derived units of a physical quantity, then what happened, we can express all the derived physical quantities in terms of these fundamental units, okay, in these fundamental units. And how we will have to express it, suppose if your area, if you want to find out area, then area is expressed as length into breadth if it is in the case of a rectangle, okay, but this breadth is also measure of length only, so we can write as length into length, okay. This length will be for that measurement of length, and for this it will be for breadth. In the case of circle also, pi r square, pi that is a constant, but r square, r comes 2 times radius into radius, so radius is also measure of length, another radius is also measure of length, so we can say length into length, okay. So if you want to express it this in terms of what your dimensions, then mass doesn't come here, so mass will be 0, length it comes 2 times, so L square, there is no time, so 0. So this area has a dimension of what, mass 0 in mass, 2 in length, 0 in time, like that. So we can simply write only L square, that is understood, okay. If there is no mass, time, then what happened, that is understood. So we can simply write as m, we can simply write this as what, simply L square, like this. That means whatever it is not coming, mass, time, the other remaining fundamental units like that of ampere, thermodynamic temperature like that Kelvin, okay, all those will not be here. If there is nothing written here, then it is understood that those fundamental units are not coming up in expressing this area, okay. And then velocity, so it will be what, displacement divided by time. So if you write only, if you take only the magnitude of displacement, then it will be distance. Distance means what, length. So length divided by time, so L T inverse, got it, T to the power minus 1, inverse 1 you can say. So what happened, this in the expression of this velocity, length will come, okay, and the time will be what, of inverse 1. So velocity has a dimension of 1 in length minus 1 in time, we can say. So from here only we can find easily about their SI units or units simply. It may be in SI units or it may be in another system of units also. So if it is in SI unit, then this area will have the unit of what, meter square, because this is of length. So length square means what, it will be meter square, because in SI unit length is measured in terms of meter. Likewise in velocity it will be what, its SI unit will be what, meter, okay, per second as inverse 1, or you can write or as what, meter per second, like this, okay. So that is how we can express this fundamental, this derived physical quantity to find its units, okay. So the dimensions of a physical quantity, okay, by knowing the dimension we can easily find out what, its units. Now this dimension shows what, the dependent of the fundamental units, okay. Yes, next is what, dimensional formula. The expression which shows that which of the fundamental units and with what power enter into the unit of a physical quantity is known as dimensional formula of that physical quantity. Now, which of the fundamental units are coming up, that means whether it is mass, length, time, thermodynamic temperature, okay, or it may be ampere, or it may be what, that mole, or I mean that amount of substance, or it may be luminous intensity, depending upon, okay, that particular subject or topic you can say. But in mechanics we require only this mass, length and time, okay, in mechanics. So what happened, we generally express it in terms of mass, length, time. But if it is in the case of what, that of electricity, then naturally your ampere, capital A, will come. In the case of thermodynamics, we may require what, the temperature, okay. So that temperature is expressed, the thermodynamic temperature is expressed as K for Kelvin, okay. Though such A, K, then mole, and then candela will be coming up if we express those physical quantity on that different branch, okay. But for mechanics we require only mass, length and time, okay. Whenever required I will tell you that one. But what is this dimensional formula? This dimensional formula is nothing but the expression that shows which of the fundamental, okay, units will be used and what is the power of those fundamental units, okay. That expression which represents which of the fundamental units are incorporated and with what power, okay, that is known as dimensional formula. So if you want to express the dimensional formula, this is only just writing as a dimension, okay. If you want to express dimensional formula for area, then you need to express it that like this: m 0 L to the power 2 T to the power 0, and then this need to be, okay, put within the square bracket. Then this expression we call it as what? Dimensional formula. Here we can simply write this as only L2, also L to the power 2 L square, okay, like this. That means mass doesn't come in area, okay, your fundamental unit mass doesn't come, your fundamental unit of time doesn't come. So what happened? Your area, the dimensional formula of area is this one, okay, L square, and it should be written within the square bracket. Now, dimensional equation. The equation obtained by equating the symbol of that physical quantity with its dimensional formula is called its what? Dimensional equation. So when I say dimensional equation means what? It will be having an equal to sign, I mean. So if you want to express your area, okay, area as dimensional equation, then let's represent it area by A. This is equal to the dimensional formula. So A is equal to what? L square, putting within the square bracket. This we call it as dimensional equation. So let me define it again. Dimensional equation, the equation obtained by equating the symbol of a physical quantity with its dimensional formula is known as what? The dimensional equation. So here it is also expressed, it is also given here as dimensional equation. So area A, if it is expressed as A, is equal to what? M0 L to the power 2 T to the power 0 within the square bracket, then this will be what? As dimensional equation. Now these are some of the dimensional formula and its units, okay. The first is also of that of area. I told you that we can write M not here, T to the power 0 also here, but if you don't want to write, it is understood that those mass time doesn't come in the expression of area, so it will be L square, and that of its unit will be SI unit will be meter square, like that. Same thing in the case of volume, it will be length into breadth into height, okay. Then its dimensional formula will be L cube and its SI unit will be meter cube, like that. Velocity, distance divided by time in magnitude, okay. So distance means length divided by time means it will be t to the power -1. So velocity has a dimension 1 in length, -1 in time, like that we will say, okay. And its SI unit will be what? Meter per second. Got it? Meter per second. Now comes acceleration. Rate of change of velocity, we call it as acceleration. So velocity divided by time, we can say. So length, okay, divided by time square. So LT inverse square. So its SI unit will be meter per second square, like that. Same thing in the case of force also. Mass into acceleration. So in this acceleration, mass will be coming up. Mass into acceleration, okay. So mass M L T inverse square, okay. So your force has a dimension of 1 in mass, 1 in length, and -2 in time, like that. Got it? So if you keep on so on like this, then you will have different what? Dimensional formula for different physical quantity. Now I told you that in the case of mechanics we require only mass, length, and time, right? But in the case of that of your thermodynamics, just like that of your specific heat, then see you will have one theta here. So different books may have different expression, okay. Here temperature is expressed as theta, but it may be also replaced by capital K also, okay. And there in the SI unit you will see that calorie per kg per Kelvin. So this per Kelvin, this per Kelvin is for this temperature, okay. How do you define how do you define your this specific heat? Specific heat may be defined as the amount of what? Quantity which is required to raise okay, which is required to raise the temperature of unit mass of a substance, this is small m, mass of the substance, through 1 degree Celsius, or through unit temperature. So that unit temperature, let's denote it by delta T. Okay, so this is what heat energy, amount of heat energy required to raise the temperature of a unit mass of a substance, okay, through unit temperature. So this is delta T. Now what happened in the dimensional formula? Heat means what? It is just like the work done and heat energy are same, okay. So its expression will be what? Force into distance, right? Work done. And this is about the mass, and this is for temperature. Let's write it like this, okay. Then what happened? Its dimensional formula, we can write it. Force is what? Mass L square T inverse. Force into distance means this will be the dimensional formula for what? This energy. Force means mass into length T inverse square, okay. But in the case of what? Your distance L, so it will be, this will be L square, okay, T inverse square. So this is about the energy, or you can say for the heat energy. And for this mass, one mass will be coming up, and for this temperature it will be Kelvin, but here it is written as theta, okay. You can use instead of this K as theta, no doubt. So what happened? Your mass will cancel in dimension. So what happened? It will be not be having any mass, so you will not see any mass in this, right? So it will be L square T inverse square theta inverse 1. For me here it will be what? L square T inverse square, and then it will be Kelvin inverse, like this. This will be the dimensional formula for specific heat. So you may not you may think that only mass, length and time is coming. Don't think like that, okay. If it is in thermodynamics, then temperature will come, okay. Thermodynamic temperature will come. And in the case of current, ampere may come, capital A may come, okay. So like that, your specific heat will have the expression of L square T inverse square and theta inverse 1, or you can say K inverse 1, okay, or simply K inverse, it will be also. Got it? Inverse means -1, we know it, okay. So like that you will have, right? But in defining this unit, okay, SI unit, you can define it from the definition also. This is what? Joule. Got it? This is joule, and then this is what? Mass. This is what? Temperature. So you can say joule per kg per Kelvin. So SI unit of what? Your specific heat is nothing but it is joule per kg per Kelvin, or you can express it in terms of calorie also, kilocalorie per gram per Kelvin, okay. Yes, so that is all about your what? Dimensional formula and its SI units. So you can pause it, this video, and you can note down this dimensional formula if you want it. But here in this velocity gradient, this should be also placed within the square bracket, okay. Yes, now let's go to that of what? This different types of variables and different types of constants. There are two types of, okay, variables and two types of constant. Constant means of whose value is fixed, and variable means of whose value is not fixed, okay. So let's divide it this as dimensional and non-dimensional. So in the case of variable also, dimensional variable and non-dimensional variable. In the case of constant also, dimensional constant, non-dimensional constants, okay. Those constants which doesn't have any dimension means which doesn't have any units, we call it as what? Dimensional. Which doesn't have any unit, we call it that as non-dimensional constant. And those which which we have dimensions, we call it as what? Dimensional constants. Now variable means of whose value can be changed, right? Like that of the area, volume, velocity, force. This has what? It can change its value, and at the same time it has its own what? Dimension. Dimension means what? Your units. Area, we express area SI unit in terms of meter square. Okay, the area of a given surface and with that of another, it will be different. The volume of one object and the volume of another object will be different, but it has what? Some numeral value as well as some what? Your letters which will represent its units. In the case of area, we express it in terms of 5 meters square, 6 meters square, 10 meters square. Got it? So of whose value can be changed, and it at the same time also it has its own unit. For volume, like that also, meter cube, velocity, meter per second, force, Newton, like that. Okay, so those physical quantity which has dimension and which doesn't have, okay, constant value, which doesn't have constant value means which has variable values, okay, changeable values, we call it them as dimensional variables. Those of non-dimensional variables, those doesn't have, okay, any unit, but it can have what? Different values, variable values. Okay, those are known as non-dimensional variables. Like that of angle. Angle between the two arms may be having different value. Specific gravity, okay, mass of the substance, okay, to the mass of equal volume of water, we call it that ratio as specific gravity of that particular body, right? So mass divided by mass, okay, we define specific gravity as what? Mass of that particular body divided by mass of equal volume of water. Okay, so what happened? Numerator is also mass of the body, denominator also mass of the water of equal volume of that given body. Okay, so mass, if you divide it, then there will not be no unit, so it has no unit at all. Strain is nothing but this is the you will learn this in your another chapter, okay, in this class 11, that longitudinal strain or linear strain. Okay, this is nothing but this is the original length to the change in length. Okay, change in length or extension or elongation. So this is what? This is also length. Even though this is an increase in length or change in length, this is also length. So length, if it is in SI unit of meter, so meter divided by meter, if you cancel it, then there will not be no unit. So your strain has no unit, just like that of specific gravity, angle. So these are known as what? Non-dimensional variables, because it has no unit and at the same time it can have varied or different values. Okay, now in the case of this dimensional constant, these are all constant, okay, but it has some unit. For example, in the case of your gravitational constant, that you learn it in your class 10, that G is equal to 6.673 into 10 to the power minus 11, right? Newton, okay, meter square per kg square, like that, right? Because your Newton's law of gravitation states that your force is equal to what? Capital G mass 1 product of the two masses divided by distance square, right? So your dimension for this, or I mean unit for this universal gravitational constant, will be what? Newton per meter square. If you come on this side by cross multiplication, so Newton meter square per kg square, this will be kg into kg, mass into mass. Okay, if you come this side, it will be divided by, so Newton meter square per kg square. Okay, so like that, it has a fixed value. Okay, your universal gravitational constant has a fixed value, at the same time it has unit. So if it is having unit, we will call it as what? Dimension. So this is the example of dimensional constant. Constant, why? Because it has a fixed value. Like that of a Planck's constant also, your Planck's constant is expressed as or use symbol as h. H is equal to 6.63 into 10 to the power minus 34, okay, joule second. Got it? So it has a fixed value, constant value, and at the same time it has unit. So we will call it such as what? Dimensional constant. For example, your acceleration due to gravity is equal to what? 9.8 meter per second square, right? So such is also what? Your dimensional constant. Like that of your velocity of light, it is expressed as c is equal to 3 into 10 to the power 8 meter per second. So such are the example of some dimensional constants, okay? So, and about that of non-dimensional constant, that constant, that means it will not change its value, but at the same time again also it doesn't have any unit. So we call it them as non-dimensional constant, those constant which doesn't have any unit, like that of some numbers 1 2 3 4, like that. And that of pi, the value of pi is what? 22 by 7, right? It will be equal to 3.142, like that, so on. So these 3.142, it has no unit. I mean for pi, it has a fixed value, constant value, and it has no unit at all. Like that of trigonometric functions, sine of what? 45 degrees equal to 1, like that, okay? It has no unit. Got it? So trigonometric functions, this pi, eccentricity e, so this doesn't have any unit, okay? And it has a fixed value, so we call it them as non-dimensional constant. Got it? Now let's try to use these dimensions and where it can be used. Let's see. And we call it this as uses of dimensional analysis. Dimensional analysis can be used as follows, okay? There are three uses. The first one is what? Conversion of one system of units into the other. For example, if you want to convert the amount of energy, okay, from the SI unit to the CGS unit, then we can use it by the help of this dimensional analysis. So conversion of one system of units into the other. For example, from CGS, okay, to what? SI unit, okay, and that 1 joule is equal to 10 to the power 7 ergs, like that, right? So ergs is a CGS unit of what? Energy. And 1 Newton is equal to 10 to the power 5 dyne, okay? That means SI unit of force is Newton. If you want to convert this 1 Newton into that CGS system of what? Unit of force, that means dyne, then it can be used. We know that, no doubt, 1 Newton is equal to 10 to the power 5 dyne. So those things, the conversion, okay, that can be done by using this dimensional analysis. Next one is what? Checking the correctness of the given physical relation. That means you are given an equation or an expression, okay, then we can check it whether that given physical relation is correct or not, okay? In a given equation, the physical quantities involved on both sides of the equation must have the same dimensions. If it is not having the same dimension, then we can certainly say that the given relation has some wrong or some mistake, okay? We can only say that there is a it is correct or not, that much only. We can't say that the given expression or given equation is exactly correct, because we can't have that if that expression has some constants, okay, then we can't say about the correctness of those constants. We can only say that the dimensional, okay, dimensionally the given equation is correct. We can say only that much, okay? If it is dimensionally wrong, then we can certainly say that the given relation is wrong, okay, if the dimensions of the physical quantities okay, or of the fundamental units involved in that relation, if they are not same on both sides of the equation, then we can certainly say that the given relation is wrong, right? But if it is dimensionally correct, then the given equation may be correct or may not be correct. Why? Because if that in that equation, if the dimensionless constants are involved, then we can't say nothing about the dimensional constants, okay, dimensionless constant, I mean. Now the last one is what? To derive the relationship between various physical quantities. Okay, if you want to express the relationship between various physical quantities, then we can derive that relation, okay, that relationship between those different physical quantities by the use of this dimensional analysis. Okay, so the first one, let's take up that conversion of one system of units into the other. Now the fact that the magnitude of a quantity is same, okay, whatever may be the system of its measurement, help us to change one system of units into another. The magnitude, okay, the magnitude will remain same, okay, whether suppose if you are going to convert that SI unit of Newton, SI unit of force Newton into that another CGS unit, okay, Earth. Now still there is what, that force will remain the force in the case of CGS unit also. So what happened? The fact that the magnitude of a quantity is same, okay, whatever may be the system of its measurement, help us to change one system of units into another. Now just to know it, that let's take okay, as an example. Now consider a physical quantity x. Suppose if x is a physical quantity, in that example, suppose if you are trying to convert the force from one system of unit to another system of unit, okay, then this x will be nothing but your force. So consider a physical quantity x. Let m1, l1 and t1 be the fundamental unit of the physical quantity in one system. Suppose if it is in SI unit, then this mass will be in terms of kg, length will be in terms of meter, and this will be in terms of second. Got it? Let n1 be the numerical value of a physical quantity in the first system. Okay, what is this n1? N1 is nothing but the numerical value of the physical quantity in the first system. Suppose if you are trying to convert this SI unit of force, okay, and we want to find out with how much amount of this SI unit of force will it be equal to the another system. Suppose if you want to find out that 1 Newton is equal to how much Earth, that means from SI unit you need to convert it into what, CGS unit, right? So while you are trying to convert, you need to know how much the numeral value is there in one system of unit for that particular physical quantity. In our case, it is Newton force. Got it? So this one will represent what, your n1. Okay, let's try to convert it in that way, and we will try to find out these numeral value also, and to the another system of unit Earth. Earth is nothing but this I'm sorry, Earth is the system CGS unit of what your energy, but it should be what, dyne, I'm sorry, dyne, okay, dyne, like that. So let's try to find it out. Okay, let n1 be the numeral value of the physical quantity in the first system. A, B and C are the dimension of mass, length and time respectively. Suppose if you are trying to express this x, then your x will be equal to what? Your x will be equal to what? Dimensional formula for this, it will be what? M1A, L1B, T1C, like this. What is set here? In the first system, A, B and C are the dimension of mass, length and time respectively in this system of unit. Okay, in this first system. So M1 has a dimension of what? A, okay, for this physical quantity. So we can say that this physical quantity X has a dimension A in mass, okay, B in length, and C in time, like that. Got it? We will try to express like this in the another system of units also. Therefore, physical quantity can be expressed as X is equal to what? N1 times of M1 to the power A, L1 to the power B, and what, T1 to the power C, like this. So this physical quantity in one system, we can express it as equal to what? N1. What is this N1? This is a numeral value of that physical quantity, okay, in one system. So let's take it this as a SI system of units, okay. So in that, I told you that 1 Newton, okay, for that one should come here as a numeral value, and A, B, C are nothing but these are dimension of mass, length, and time in that first system of unit, or rather you can say in SI system of units, okay. Now we will try to express it this in another system of units. So M1, L2, T2 be the fundamental unit of that particular physical quantity X in the second system of units. Okay, let's take it this second system, for example, as CGS unit. In that example of 1 Newton to dyne, we want to find it out. Okay, Newton is what? SI unit, and then dyne is CGS unit. So that 1 Newton, 1 is coming up here, and we need to find out the numeral value in the another system, how much it will be coming. Okay, N2. So it's N2, it's its numerical value. Therefore, X can be also expressed in that second system of unit as N2 times of what? M2 to the power A, L2 to the power B, okay, T to the power T2 to the power C, where A, B, C are the dimensions of mass, length, and time. Okay, so these dimension will never change, okay, when we change the system of units. Okay, for this particular, suppose if it is force, then what happened? This will be what? M L square T in M L T inverse square. Okay, so that M1 L1 T inverse square, that will remain same, okay, whenever you change from one system to the another system of units. Okay, so likewise your ABC in the first system of unit, the dimensions of mass, length, and time, the dimension of mass, length, and time in the another system, this will also remain same. That means dimension will never change for a particular physical quantity if you change the system of units. Okay, whether it is SI unit, whether it is CGS unit, the dimension will remain same provided it is for a particular physical quantity. Okay, so now then this also is a physical quantity, this is also the physical quantity, same physical quantity, so we can equate this, okay, their right hand side, okay, in one system and second system. So when you equate it, then it will be coming up like this. Okay, so what happened, you may express this N2, we want to find out this N2. N2 will be equal to what? N1 times, you try to transfer this M2 L2 on the other side. Okay, M2 L2 T2 on this side. Then what happened? M1 and M2, they are having the same dimension, so we can express it these as what? M1 by M2, okay, L1 by L2 to the power B, T1 by T2 to the power C. So we can express it these as what? N2 is equal to N1 all into what? M1 divided by M2 to the power A, L1 by L2 to the power B, T1 by T2 to the power what? C, where A, B, C are dimension in mass, dimension in length, dimension in time. Got it? So in that case of the example that I have cited, okay, let's see. Okay, I will not write it here, but rather there will be an example there in the next slide. Okay, let's try to see it. Now see, convert 1 joule into hours using the dimensional analysis. Okay, joule is nothing but this is the unit of work or energy, you can say. Okay, so in SI unit it is what? Joule. In SI system of units, your joule is the unit of work or energy, you can say. So dimensional formula will be what? Force into distance. So your force is what? Force is expressed as what? Mass, length, this one, mass into acceleration. Got it? So this is the dimensional formula for what? Force. Okay, so force into distance. So another L will be coming up for distance if you are going to express it as what? Work done or energy. Got it? Then what happened? This will be equal to what? The work done or the energy will be having what? M L square T inverse square. From where this L square comes? 1L is coming up here. Got it? So force into distance. Force into distance. So it will be having this dimensional formula here. Got it? So this is a dimensional formula for work. And let's take it that A here, A is a dimension for M. Okay, A is a dimension for M, B is a dimension for length, and C is a dimension for time. So A will be equal to 1, B is equal to 2, and C will be equal to -2. It is given here. Okay, so to convert it, let's not go like this. Instead, let's go directly there like that. What was that in the formula, last formula, that if you want to convert it, then it will be N2 will be equal to N1 times of what? M1 divided by M2 to the power A, like that. Okay, L1 divided by L2 to the power B. Same thing if it is T1 by T2 to the power C, like that. Okay, so in our case what happened, this is, we want to convert this 1 joule. So your 1 joule is equal to how much, right? So your N1 will be equal to 1. Got it? So your N1 is equal to what? So let's write it that by using this formula. Let me remove it, this one, so that what happened, it will be equal to N2. Here it is given as N2 is equal to 1. 1 means what? That of this N1, 1 joule. Okay, so this will be all that of the first system of unit. Let's take it here as SI unit. So in the case of SI unit, mass will be in terms of kg. So 1 kg divided by 1 gram. Okay, in the another system, this is CGS system, ours is in the CGS system, so it will be, mass will be of that of 1 gram. On this side, length will be 1 meter. In CGS, it will be 1 centimeter. So in the case of mass, it will be 1 kg divided by 1 gram to the power 1. Why? Because A is equal to 1. Got it? Dimension of mass is 1, and dimension of length will be what? 2. So you need to put it that 1 meter divided by 1 centimeter here, square. Time will be same. In SI unit also 1 second, in CGS also 1 second, but the dimension is -2. So if you do all this simplification and if you cancel it, then you will get it as 10 to the power 7. This 10 to the power 7 is nothing but this is a numeral value in the another system. Okay, in CGS system, N2 will be equal to 10 to the power 7. So we can certainly write 1 joule is equal to what? 10 to the power 7 earths. Got it? So likewise, we can use it for conversion of, okay, any physical quantity from one unit to another unit. You can also convert it from CGS system to what? SI unit also. Okay. Next, let's try to see about the checking the correctness of the given physical relation. Okay, this is the second application of this dimensional analysis. But before that, let's try to know what is meant by this principle of homogeneity, because we are going to use this principle of homogeneity in checking the correctness of this given physical relation. Okay, the second application, I mean, this principle of homogeneity states that the dimensions of the physical fundamental quantities of two sides of a given physical relation must be same. Okay, this principle of homogeneity, homo means same, geneity means of that of what, equality or what, uniformity. Got it? In dimension, we call it that as principle of homogeneity. Suppose if you are given a physical relation or equation, then you need to see the fundamental quantities involved in that expression, and the fundamental quantities, okay, the dimension of those fundamental quantities involved on both sides of the given equation must be same, and that principle is known as principle of homogeneity. Got it? Suppose if you are given that in one relation like this, m to the power x, l to the power y, t to the power z is equal to m to the power a, l to the power b, t to the power c. Okay, these are the fundamental unit: mass, length, time. Mass, length, time. Okay, on the left hand side, the dimension of mass is x, dimension of length is y, dimension of time is z. On the right hand side, likewise, mass a, dimension of length b, dimension of time is c. So this principle of homogeneity states that what happened, the dimensions involved on the physical quantities or fundamental units on both sides must be same. That means this mass x, the dimension on one side, must be having the same dimension on the other side of this physical fundamental unit m. Mass should have same dimension, length should have same dimension on both sides. So x must be equal to a, y must be equal to b, and z must be equal to c. That is what, dimension of mass, length and time must be equal on both sides. Got it? So by checking the correctness of a physical relation, we are going to check nothing but we are going to check whether the dimensions involved in this physical fundamental units on both sides, are they coming out to be same or not. If they are coming out to be same, then the physical relation, we can say that that is correct dimensionally. Okay, if that is not correct, that means if the dimensions are not same on both sides, then we can certainly say that the given relation is not a correct relation. Got it? But if it is correct, if dimensions involved in the physical fundamental units are same, then we can certainly say that the dimensions, the given relation is dimensionally correct. I'm repeating it, dimensionally correct. Okay, it is correct dimensionally, but we can't say nothing about that of the constants. Okay, let's see about the application or the actual word application in terms of some given formula. Let's see. Check the dimensional consistency in the case of the following equation. Is Fs is equal to half mv square minus half mu square. Okay, where symbols have their usual meanings. Okay, so now what happened, this is force into distance. This is nothing but this is the work done. Okay, there is a formula known as work energy theorem. Work is equal to what, change in kinetic energy. That formula is here. So now let's try to see whether this given relation is dimensionally correct or not. Now we need to write it, this force and distance, their dimensions, okay, separately, mass also separately, velocity also separately, like that. Then what happened, you need to write it, these dimensions separately, and then what happened, we need to see whether the dimensions involved in these fundamental units are coming up okay, in these given relations are same or not. Now when we see that this left hand side is force into distance, and the right hand side will be what, that of the velocity and the mass. Okay, but half is being constant, we have no dimensions for them, so we are not writing it. Okay, now let's see this mass, okay, L square, right? So L into L will be L square, right? So this one, L into L will be L square, so it will be having what, m L square T inverse square. Now see, when you compare the dimensions for mass on this left hand side, it is also 1. On the right hand side, these are also the terms involved here having also mass 1 1 each. So mass has a dimension 1 on every terms involved in this given equation. Okay, and here in length it is 2, dimension is 2, here also 2, here also 2. So time also minus 2 minus 2. That means the dimensions involved in this fundamental unit of each term is what? Same. Okay, m1 1 1, l2 2 2, t minus 2 minus 2 minus 2. So that means this given relation is dimensionally what? Correct. Okay, then to derive the relationship between various physical quantities, if we want to derive the physical quantities, then we can derive it by using this dimensional analysis, and this is the third and last application of dimensional analysis. Okay, by using what? By using dimensional analysis, we can derive the expression of a physical quantity using the principle of homogeneity of dimension. Okay, if we know the various factors on which a physical quantity depends, if we know that this given physical quantity depends on some factors, so by knowing all those factors we can easily find out the relation between the given physical quantity with the different factors, okay, which depends on it, right? So now this is simply the statement for this one, and let's try to see with some example to illustrate it. Okay, now let's see as an example. Okay, derive dimensionally the expressions for the centripetal force F acting on a particle of mass m moving with velocity v in a circle of radius r. Okay, so that means this is nothing but this will be the expression for centripetal force. So your F is directly proportional to the mass. We know that if mass is there, you must be knowing the relation of centripetal force as F is equal to mv square by r. Okay, so what happened? Your force is directly proportional to mass, as it has been said here. So m to the power a, it depends on v also, b to the power b, it depends upon radius r also, so r to the power c. Or if you want to express this directly proportional into equality, we require a constant k. So m to the power a, b to the power b, r to the power c. With that k we have written like this, where k is a proportionality constant and it is also a dimensionless constant. Okay, that means it is just like a constant. Now we try to express this in terms of their dimensions. Force, we know that this is ml t inverse square, mass into acceleration. Acceleration means rate of change of velocity, right? So it will be lt inverse square for acceleration. Mass is m. Now here on this side also you try to express it that mass is capital M, so to the power a, because its dimension is a. Now velocity lt inverse whole to the power b, because velocity has a dimension b. Likewise L also c. L, this r is the length, so like that. So what happen if we simplify it, then it will be what? Mass a, and L will be what? Here power is b, here c, so b plus c will be coming up for length. Likewise for time it will be minus b. Now we need to equate it. This dimension of mass for this given physical quantity, mass is 1. So we need to equate it 1 with that dimension of mass on the right hand side. So your a will be equal to 1. What about this for length? So b plus c will be equal to 1. We need to write it like that. B plus c will be equal to 1, because the length on the given physical quantity for dimension of length will be what? 1. So here on this right hand side, b plus c will be equal to 1, like that. Okay, we need to write it. And for minus b, it will be equal to minus 2. So your b will be equal to 2. So if you put that b is equal to 2 in this above relation for that of dimension of length, then what happen? You will get c is equal to minus 1. So we can certainly write the given expression f is equal to k times of m to the power what? A is equal to what? 1. So a will be having only power 1. Whereas b is equal to what? B is equal to b. We found that b is equal to 2. So b square. What about the c? C is here as minus 1. So minus 1. So we found that your centripetal force is equal to what? K times of mv squared by r, which is the expression for the centripetal force. So likewise, we can find out the expression of the given physical relations if we know the different factors or different physical quantities upon which it depends on. Okay, so this is the example or illustration of this third application of dimensional analysis. Got it? Now there are some limitations for this dimensional analysis. What are those limitations of this dimensional analysis? We can this is generally asked also in the what examinations also. In spite of the fact that dimensional analysis has many uses, it suffers from the following limitations. Okay, the first one is what? Dimensional constants involved in the physical formula cannot be determined. We can't determine that of half, okay, whether of 3 by 2 or 2 times if it is coming here. So we can't determine it, those dimensional less constants, whether it is correct or not, which is given in the equation. For example, in this given equation, we know that this given relation S is equal to ut plus half at square. We know it that this is a correct relation. Okay, but if one has written wrongly that S is equal to ut plus twice at square, and if you check it whether this given equation is correct or not, dimensionally it will be correct. Okay, instead of this half, if you are having 2 also here also, dimensionally it will be correct. So we can't say whether that dimensionless constant involved in the physical formula, okay, we can't say that whether it is correct or not. The dimensional method fails to derive the relation like S is equal to ut plus half at square. Those dimensional those formula which has constants, okay, we cannot derive it. Okay, we can derive it. If we derive it, this relation, then S will be equal to ut, okay, plus at square. We can derive it in that way, but not this half. Here also b square minus u square is equal to twice as. We can't derive it such relations involving what dimensionless constants. Okay. Number 3, it fails to give informations about the trigonometric functions, logarithmic functions, exponential and complex quantities involved in the physical relation. We can't say about what the informations, okay, about these trigonometric functions, logarithmic, exponential and complex quantities involved in the physical relations. Okay, because this has what different what dimensions, or it may be also dimensionless. If it is having that of trigonometric functions, then it will not have any dimension. Got it? If it is logarithm, also same thing. Got it? So such trigonometric functions, logarithmic functions, exponential and complex quantities are involved, then we can't give any informations about this. Okay, so it fails to give informations containing about trigonometric functions, logarithmic, exponential and complex quantities. Okay, since there are only 3 quantities, namely mass, length and time, where powers can be compared on 2 sides of equations, therefore the dimensional analysis failed to derive the relation involved more than 3 independent factors. Okay, we can't use that of ampere, we can't use that of thermodynamic, temperature, Kelvin. Okay, we can only derive only those having only these 3 fundamental quantities, mass, length and time. Okay, and which are also independent, right? Because of that, we can derive it by using only 3 independent, okay, these physical quantities only. Over and above this, if we have more physical quantity like that of Kelvin, okay, like that of thermodynamic temperature or mole, okay, all those, if it is over and above this M, L and T, then we can't find it out. We can't use it to find out the relation involving those physical quantities. Okay, the last one is what? A dimensionally correct relation may not be true physical relation, as I said in the beginning. Okay, because the dimensional equality is not sufficient for the correctness of a given physical relation. For those involving those constants, those trigonometric functions, we can't say anything about it. So we can only say that if dimensionally it is correct, okay, if dimensionally it is correct, then we can say that the given equation is dimensionally consistent, that means dimensionally correct. Okay, that much we can say. But if the given relation or equation is not consistent with dimension, then we can certainly say that the given relation is a wrong equation or relation. Okay, so those are the limitations of dimensional analysis. With that, we come to the end of this today's class. Thank you.